everybody, welcome to video 97.2. We're going to be able to solve a variety of Stoich problems. We could use moles, mass, particles, volume, and heat. So get ready to change. Right. Just to review, stoichiometry is the study of the quantitative or numbers aspects of chemical reactions. Amounts. Look at that. Cool, right? Alright, so make sure you read section 12.2 in your book. There's the page numbers. Find lots of interesting stuff there, right? Okay. Just to get started, if you were making tricycles, now that's a good tricycle, here would be the chemical formula for it. Alright, you need 3 wheels and 1 frame for every tricycle. So what if we had an infinite number of frames, as many frames as you wanted? What's the most, how many tricycles can you make with 9 wheels? Well, you could say, well, I'm start with 9 wheels, that's what I'm given. What am I trying to find is find tricycles. So I could say, well, I want to change my wheels into tricycles. And then you look at the equation, you say, well, I need 3 wheels for every 1 tricycle. So guess what I'm getting? I'm getting 3 tricycles, and I am going to ride, woo! Okay, so what we do in chem is we use moles to moles as coefficients. That's how we change wheels into tricycles. So if you're given 12.3 grams, all right, so you got to be able to look at the problem, find out what it is you're given, 12.3 grams of potassium chlorate. How many grams? So given grams of KClO3, we got to find grams O2. We have to change the identity of this stuff into this stuff. But the only time you can use these coefficients is when you have moles. All right, so we're going to have to take this first step and change the grams of potassium chlorate into moles of potassium chlorate. And then we are ready. We are ready to change. It's time to change, man. Change the KClO3 into O2. But notice what units it has to be. It has to be moles. Moles of each. And then, will we be done? Nope. Because we're trying to find grams of oxygen. So we're going to have to change those moles of oxygen into grams of oxygen. Okay, let's get busy. If I want moles to grams or grams to moles, it's KClO3 the whole time, so I can say 1 mole equals, and I go get the grams from the periodic table. Find out that's 122.55. Okay, periodic table. Now I'm in moles and moles, and look at the identity is changing. The only place you can change the identity is using moles, and you have to use coefficients. What's in front of the oxygen? 3. So there's 3 moles of oxygen in the balanced equation for every 2 moles of KClO3. So these are the coefficients. That's the mole ratio, right? Mole ratio. All right, but we wouldn't be done because our answer needs to be in grams. So then we go back to what we learned and say 1 mole equals 32.00 grams of oxygen. Bye-bye potassium chlorate gram. See you later, moles of potassium chlorate. Adios, moles of oxygen. We're going to be left with grams of oxygen. And so we do 12.3 divided by 122.55 times 3 divided by 2 times 32. And when we plug that all in, we find out that there are 4.82 grams of oxygen. But what does this mean? Well, it means if we're in the lab and we put in 12.3 grams of this, we could expect, if everything works perfectly, to get 4.82 grams of that. All right, so here's a little road map you can do. This is your known or your given. All right, we could call it substance A, right? And if we're trying to find, what are we trying to find? Substance B. We got to change the identity of a chemical. Where do we do that? We do that at the mole ratio. Moles of A need to change to moles of B. But before we could do that, we have to get moles of A. Now, in order to get moles of A, we could change volume of A into moles by using 22.4. We change the mass of substance A into moles by using grams from the periodic table. We can change atoms, molecules, or formula units into moles by using Avogadro's number. Okay, but once we're in moles, we can use that mole ratio where we have to use the coefficients. If you want to draw this diagram in your notes, it might help. And then when we use the coefficients, we turn it into moles of another substance. But if the answer, I don't know if you can hear that, there's a train going by. But if you want your answer in atoms, molecules, or formula units, then you have to use Avogadro's number. If you want it in mass, you have to use grams from the PT. But guess what this is? This is all about B, substance B. All right, it's all about B. So you get grams of B here. Over here, we'll get liters of B. All right, so This was the moles from last chapter. This was moles from last chapter. But if you put it together using that mole ratio, you can change one kind of mole into the other. Let's try it again. All right, so if we have, actually, you know what I want to do with this one? I want to save this one for class. Okay, so save this one for class. If you want to write this into your notebook, then when I do this example in class, you'll know which one I'm talking about. Okay, let's practice another one. Also use this, and what I'm going to do for this one is I'm going to tell you the answer is 1.24 liters of O2, so then you could try it using conversion. Okay, let's try this one. This time we're given, so this is our A, given molecules of O2. What are we trying to find? How many liters? Find liters of CO2. Oh, we have to change its identity, so we got to change this into this. A good thing, they're both in the balanced equation. But before we can change one of these into another, we have to be in the moles. So we take 5.67 times 10 to the 23rd. That's molecules of oxygen. And we want to change molecules of oxygen into moles of oxygen. And then we are ready to make the big change of one substance, oxygen, turning into the other one, carbon dioxide. But are we done? No, what we're trying to do is find, so we got to change those moles of carbon dioxide into liters of carbon dioxide. Okay. So we're changing the identity at the mole ratio step. So what do we got to do first? We got to get rid of the molecules. So we use Avogadro's number of molecules of oxygen for 1 mole. And then for the mole-to-mole step, we need coefficients. What's in front of the O2? A 1. What's in front of the CO2? 2. Okay. Then we're back to mole conversions. Moles to liters of carbon dioxide. 1 mole has 22.4 liters of carbon dioxide. All right. Goodbye, molecules of O2. Goodbye, moles of O2. Hello, carbon dioxide. Finally, liters of carbon dioxide is what we're going for. And if we do that, we get 42.2 liters of carbon dioxide. All right. So make sure your units are canceling. Make sure you're left with with what you're trying to find, and you start with your given. Okay. Let's try another one. Oh, look, there's a little road map could help us. All right. This one involves a little the heat coefficient that we were talking about. How much heat? Find kilojoules, because that's what heat's measured in, kilojoules. Find kilojoules. Is required to use 58.6 grams of potassium chlorate. All right, so this is given, grams of KClO3, find kilojoules. Okay, so our plan should be take the given 58.6 grams of KClO3, and then we have to change grams of KClO3 into moles, because the only way you can use the numbers in the balanced equation is if you're in moles. All right, so this is the heat that belongs with this reaction. So I want to get rid of the moles of potassium chlorate and change it into the heat. But now I got to go back and use the coefficients or numbers from the balanced equation. 195.3 goes with kilojoules. Okay, what goes with moles? Well, we have to find KClO, potassium chlorate. Here it is. What's in front? A 2. Okay. And going back here, this is all potassium chlorate. So we know 1 mole equals, go get it from the PT, and 122.55. I added up KClO3. So bye-bye grams of potassium chlorate. Bye-bye moles of potassium chlorate. Hello, kilojoules. All right, and then we look to see, calculator that divided by that times that divided by that. We find out you get 46.69 kilojoules for that reaction. Okay, this one I want to save for class. So go ahead and copy that into your notebook, and then we'll do that problem in class so that we have another example. I said it, another one. Okay, all right. Hey, look. This time we are given silver nitrate. Oh wait, let me get rid of that. I'm backing up. You didn't see that. Given, all right, given mole of AgNO3. Moles of silver nitrate, that's our given. How many grams? Find grams of Ag. So let's get started. You might be saying to yourself, wait, here's silver nitrate, here's silver. How can we change one thing into another? We need a balanced chemical equation. Boom. Okay, so usually I'll give it to you, but you could do this yourself. Silver nitrate plus lithium gives you silver plus lithium nitrate. Make sure it's balanced. 1, 1, 1, 1, 1, 1, 3, 3, done. So all the coefficients are 1. So I'm given moles, 2.6 moles of silver nitrate. Hey, it's Silver Surfer down there in the corner. So once I'm in moles, I don't have to use the periodic table here because moles can use the balanced equation. So I could say moles of silver nitrate straight up right away can turn into moles of silver. Okay, so this turns into this. But what do I want? I want grams. So then I do have to use one more conversion. And now I can put in some numbers. Moles of silver to moles of silver nitrate. Moles of one kind and moles of another. Coefficient, 1, 1, done. Moles to grams, you have to use 1 mole, and then you have to go get grams from the periodic table. 107.87. Okay, that is the molar mass of silver. Okay, goodbye silver nitrate. Hello silver moles. Goodbye moles of silver. Hello grams of silver. And then you do 2.6 times 1 divided by 1. Don't need to plug it in. Times 107. So you get 280.46 grams of silver. Okay. This time you started with moles already, so you can convert to new moles using the balanced equation. Okay. Oh, look, given here we were given A in moles, so you just have to mole ratio and then one step out for grams. All right. Please review with me here. Always go through moles. All right. Use moles over moles when you want to change the identity, and that's using the coefficients. All right. You can change reactants to products. You can change products to reactants. You can change reactants to other reactants. You can change products to other products. You can change reactants or products to heat and heat to either of them. It doesn't get more exciting than this. Okay, these are stoichiometric calculations, and you can cheer for them. All right, and make sure to read section 12.2. All right, and don't be afraid to change. All right, because it's all about the mole ratios. Peace out. Oh, I need to stop.